Hi there, Mr. Sutton here, bringing you a lesson on similar polygons. In this one, we'll find missing measures of these similar polygons, and specifically, we'll use similarity to find the perimeter of a new pool based on the dimensions of the old one. For the warm-up on this one, what does it mean for two polygons to be congruent? All right, let's see what we came up with. So congruent polygons have two things going on: the same size and they have the same shape. So for example, these two pentagons here, or all of these different hexagons, same size and same shape. Now that we've reviewed congruence, let's talk about something that is similar but not quite the same, namely similarity. Similar polygons have corresponding angles that are congruent. They're the same angles, in other words, and corresponding side lengths that are in the same proportion. So the same angles means we have the same shape, but the side lengths in proportion means that we don't have the same size necessarily. We have different sizes with the same shape. So for example, triangle ABC and triangle DEF. Same shape, same angles, different lengths. Let's talk about the notation of similarity. So we have this little squiggly symbol here. We can say that triangle ABC is similar to triangle DEF using this symbol. This, by the way, is called a similarity statement. Now, the important thing to know about similarity statements is that the order of the letters in the similarity statement tells you which angles and sides go together. For example, since A and D are the first letters in each of these statements, that means that angle A is congruent to angle D. And since BC and EF are the second and third letters of each statement, that means that those sides, BC and EF, that's BC over here and EF over here, those sides are in proportion. Now, if two shapes are in proportion, it means you can multiply all the lengths of one shape by some number, and it would give you all the lengths of the other shape. The ratio of the two shapes' sides we call the scale factor. So if you take the lengths of, for example, triangle ABC and compare them to the lengths of triangle DEF, you'll get a scale factor. Since, for example, side AB is 10 and the corresponding side DE is 20, 10 to 20 means we have a 1 to 2 ratio. All the sides of a triangle ABC are half the length of all the sides of triangle DEF. Now, scale factors, it depends on which order we're going here. ABC to DEF is 1 to 2, but if we go the other way and ask the scale factor of DEF to ABC, well, now we're doing a 2 to 1 ratio, so the order does matter. Let's do some problems now involving similarity. Let's say we have a diagram with triangle DEF being similar to triangle MNP. Based on that, they want to know the values of x and y. Let's do the easiest part of this first. So we know that similarity means that angles, corresponding angles, are congruent. So we can at least figure out y right away. Which angle does y go with? Well, in the similarity statement, E and N are second letters, so we can say that E and N are congruent as angles. So that means that y then has to be the same as N, 35 degrees. Now, you could say, oh, well, it looks like it's the same angle in a different triangle based on these pictures, but you have to be careful because they don't always orient the triangles the same way. So it really is good if you have a similarity statement just to be on the safe side. Let's turn our attention to the other part of this problem now, which was solving for the value of x. X is a side. For sides, we're going to set up and solve a proportion that has the missing side, its corresponding side, and one other pair of corresponding sides that we already know. So we have a side that we already know, 9 and 12, we already know that. That can be side 1 and corresponding side 1. And for side 2, well, that's the x side that we're looking for, and its corresponding side, which is this 20 side over here. So we can say 9 over 12 equals x over 20, or vice versa, it doesn't really matter. Cross multiplying, we have 12x equals 180, and dividing by 12, we get x equals 15. Here's another similarity problem, this one involving quadrilaterals. Pause the video and try to find the value of A, B, and C. Okay, let's see how you did. For A, we need to set up a proportion. A corresponds with this 40 side over here, And again, we know that not just because they look like they're the same side, but also because F and G, that's the first and fourth letters, and Z and Y for this side is also the first and fourth letters. Again, the similarity statement tells you which angles and sides go together. So we can say A over 40 equals 40 over 32. We have to use 40 and 32 because those are the only two other corresponding sides that we have a value for both of the sides. Cross multiplying, we've got 32A equals 1600. And dividing by 32, 160 over 32 would be 5, so one more 0 gives us 50. Let's find B now. We can say B over 16 equals 40 over 32. And we actually also could have used 50 over 40 now that we know the value of A. I would actually advise against that, though. There's a chance you messed up the value of A, but you know 40 and 32 are correct for sure. So it's always good to hedge your bets so you can at least get this part of the problem right, even if you messed up this other part. So we can say, let's see, that'd be 640 equals 32B, and then dividing, that'll be B equals 20. Now for C, angle Y corresponds with angle G. Those are both fourth letters in the similarity statement, so we can say C equals 49. Let's talk about similarity for things other than just the sides of a shape. It turns out that according to the all lengths are similar theorem, that's not really the technical name, but that's what it amounts to. When you have similar shapes, that means that everything about them that involves distance is similar, including perimeters, medians, altitudes, pretty much anything that's length-based. So for example, in these two shapes, we can say that the perimeter of this first shape divided by the perimeter of this other shape is going to equal the scale factor. Any similar sides, when you put them in a fraction, they are going to reduce to the scale factor. That, again, is what the scale factor gives us. It's the ratio of one side of a shape to the corresponding side of the other shape. We're going to do a problem now where we get to test the all lengths are similar theorem out. So for the first part of this, go ahead and find the scale factor of ABCDE to FGHJK. You got it? So we need to take two sides that are corresponding from these. The only two sides that we have are this 10 and this 15 side. And again, just to double check, A and B, second and first letters, F and G, second and first letters. So then the scale factor of the first shape to the second shape is just going to be 10 to 15, or 2/3. Next, they want us to find the value of x, which is side AE over here. So we're going to set up a proportion. We can say that x over 18 equals, and you have some options here. You could use 10 over 15. In general, you can just use the scale factor if you already have it whenever you set up any kind of proportion. So we could say x over 18 equals 2 over 3. So 3x equals 36, and x equals 12. Next, they want the perimeter of ABCDE and the other shape. Probably the easiest way to do this, although they list the smaller shape first, would be to find the second perimeter because they actually gave you all of those sides. So if we add all the sides of that larger shape together, I'm going to plug that into the calculator here. All of that comes out to 69. And now that I have the perimeter of the larger shape, since I know the scale factor of the smaller shape to the larger one, I can set up a proportion to find out the perimeter. And just to make my life a little bit easier, I'm going to set up a variable, we'll call it P, that equals the perimeter of this smaller shape down here. So I can say P over 69, the ratio of the smaller to the larger perimeter, equals our scale factor of 2 to 3. Cross multiplying, this is going to be, let's see, 2 times 69, which is 138, equals 3p. And 138 divided by 3, that's going to come out to 46. For the wrap-up, here's a problem for you to try on your own. Let's say a town is building a new swimming pool. An Olympic swimming pool is rectangular with a length of 50 meters and width of 25 meters. This new pool the town is building will have a similar shape, but only be 40 meters long. Pause the video and see if you can find the scale factor of the new pool to the Olympic pool. Then, find the perimeter of the Olympic pool and the new pool. All right, let's see how it went. So for scale factor, we need a side that corresponds from each of these pools. The only length we know, or the only measurement we know for the new pool, is the length itself, so 40 meters, and that corresponds with the 50-meter length of the Olympic pool. So new pool to Olympic pool, that's going to be 40 to 50, which is 4/5. Next, finding the perimeter of the Olympic pool first. We've got twice the length times twice the width, so 2 times 50 plus 2 times 25. That's 50 and 100, or 150 meters. And now we'll set up a proportion. Let's call the perimeter of the new pool just P. We can say that P over 150 equals our scale factor of 4/5. So that's going to be 5P equals 600. Dividing by 5, we get P equals 120 meters. So that's it for now. Hopefully you have a better understanding of similarity and swimilarity. Until next time, this is Mr. Sutton signing off.